You have a Taylor series formula centered at A. The formula reads the summation of the nth derivative at center A, all being divided by the n factorial, times a quantity of x minus that center, and that is all raised to the n as n goes from 0 to infinity. So now what? How do you represent different functions using Taylor series? Let's use probably the most popular one to know, e to the x. And we're going to center at 0 because the one thing we do know is that e raised to the 0 will always equal 1. So if you're going to begin your Taylor series representation, you literally have to begin n at 0, which means you're going to take the original function. You're not going to take its derivative, which ironically in this case is not going to make much of a difference, but we'll get to that in a moment. Taking the f of x, e to the x, you're going to plug in that 0, which is your center, and you're going to get 1, which is right here. You have to take that value that you have right here, which you put here, and you divide it by the 0 factorial, and you get 1, and then you take that number and you multiply it by x minus 0, that quantity raised to 0 is 1. So 1 times 1 is 1. You've done your Taylor series representation of e to the x for the 0th order, which is completely and really quite useless because what over here I'm going to show you is every prediction that you make is going to be a prediction for, let's say, 1. E to the first will be 1. E to the second will be 1. Let's slide this back over here. E to the negative 1 will be 1. And e to the negative 3 will be 1. Where the red graph is the actual answer and your blue graph is essentially the same answer every single time, not exactly a very helpful approximation. So what do we usually do? We did a first order representation. Now you're going to say, I don't recall we call it first order. It's because we refer to it as a linear approximation. We've referred to them as tangent line approximations. And now we're going to start referring them as first order approximations because literally our largest degree term will be x to the first. And how do we generate that? It's time for us to take the first derivative of e to the x, which is e to the x. And you're going to plug in that center 0 into that problem and you still get 1. And then you still take that 1 and you divide it by, okay, at least now it's 1 factorial. And you get 1, and then you multiply it now by at least to x, and so that's how you get x. And so now you have a linear equation that is going to do your approximate. Now, at 0, the answer is exactly the same, but at least when we start making approximations for, let's say, e to the first, we get a different value than we did before. Now we have a value of 2 because literally 1 plus 1 is 2. Now it's not this actual answer of e, but it's not a bad approximation. Of course, the farther out we go, let's say e to the second, that error between here and here increases. Of course, we could go back to negative 1. Let's do that right here. Well, that's a pretty good approximation. It says it's 0 when it's actually 0.36. But again, if we go back, oops, go the other direction, yeah, we're getting farther off. So how do we improve upon it? And that's the beauty of a Taylor series representation. We can improve upon it. We can take the second derivative because we know their first derivative is going to be changing due to a second derivative, and we could work that out. So let's go back and set this back to 0, which is right there, and let's go ahead and find the second derivative now, which still is e to the x, which is still 1. Now, you have to take that 1 and divide it by 2 factorial. Now, in this case, 2 factorial is 2, which is pretty easy to remember. And then you multiply it by now x squared. And so what you see is the blue graph is now a quadratic approximation. You're using a parabola to approximate this curve. So if I plug in 1, you're going to see my approximation has gotten significantly better because the quadratic curve is fitting the e to the x curve a little bit better, at least as we're close to our center. And now I'm getting a value of 2.5. How am I getting that value of 2.5? Well, let's see if I can get this to work properly. Over here, let's see, I'm going to be plugging in e to the first, so it's going to be 1. Then I'm going to add another 1, and then I'm going to add 1 squared over essentially 2, and that's how I get 2.5. And there we go. We can actually keep improving upon this by going ahead and taking the third degree. And if you look here carefully, you will see that it's going to now be x cubed over 3 factorial. And my error is a lot less because my approximation is better. And this cubic is fitting the graph better. And I can keep going down the line, the 4th order, and then the 5th order, and the 6th order. And as you can see, the blue curve keeps approximating the e to the x curve better. And again, let me emphasize that I could get this approximation if I would just keep working it out, going plus 1 cubed over 3 factorial. And this is one of those times where I think it's easier to see it as factorials instead of the decimals, because if you look at the fractions, let's turn that off, you'll see that 6, 24, 1, 27, 20, unless you know your factorials, it's probably easier just to leave them as the factorials. 1 to the 4th gets divided by 4 factorial. 1 to the 5th gets divided by 5 factorial. 1 to the 6 gets divided by 6 factorial. Not the neatest, but you get the general idea. And so I'm just going to kind of play this out to the end. And as you keep increasing your nth order, and I just got rid of the table at this point, you should have by now kind of seen a pattern. This e to the x seems to be x squared is divided by 2 factorial, x cubed is divided by 3 factorial. And what we do is we can summarize it literally by going x to the n over n factorial as n goes from 0 to infinity. And that is the e to the x formula. And this here tells you the interval convergence, which tells you that you will be able to approximate e to the x for any real number. And so that's how e to the x works. So let's look at a different variation of e to the u. In fact, in this case, let's make f of x equal e raised to the 2x. And we'll go through the Taylor series steps again. We'll start with n being 0, which means we take our original function, e to the 2x. We put in our center of 0, which we get 1. We take 1 divided by 0 factorial. We multiply it by x raised to the 0. We get 1. And literally, again, we start all over with a constant approximation of 1. If we make it into a linear approximation, remember to apply the chain rule when doing the derivative, and now you'll get 2 times e to the 2x. So if we do plug in the 0, we're going to get 2 times 1, which is 2. We take the 2 divided by 1 factorial and multiply it by x, and we come up now with 1 plus 2x, a different equation than we had before. And so as we approximate, let's go back to 1, you will notice that e to the, which in this case would be 2 times 1, or e to the second, works out to roughly 7.38905. E to the second using a Taylor approximation is literally 1 plus 2 times 1, which is 3. So we're going to continue on. We're going to go e to the second, and we're going to go e to the third, and e to the fourth, and you can see coming up with these different values. So I get this Taylor series representation down here that's done automatically through GeoGebra. It's not exactly easy to visualize, so I thought I would try rewriting it. And maybe the first thing I might consider doing is removing the factorials, simplifying the fractions. And let's see what I rewrite. I'll put that on top here. Let's start with 1. It's supposed to be a 1. Plus 2x, so nothing changes there. Plus 4 gets divided by 2, which would then be 2x squared. Okay, I can see that. 8 over 3 factorial. There's a 2 in the 3 factorial that goes into 8. Yeah, I can see now that how it ended up being 4/3 x cubed plus 2/3 x to the... No, I'm not really seeing a pattern here. Maybe it wasn't so wise to stick with the changing the factorials out. Let's go back to them and change them out. And let me change the color to red, make it stand out a little bit. So let's try this again. 1 plus 2x. Now I get 2 factorial in the bottom. Let's see, if I write 2 factorial here, you know, what I could do is I could write 2x quantity squared in this spot, because 2 squared is 4 and x squared is, well, x squared. And you know, I could actually have done that here as well with 2x quantity cubed over 3 factorial. And the next term could have been 2x. Oh, I see a pattern here. I see a quantity of 2x being constantly raised by n and then divided by the n factorial. So if I would go back to my original e to the x Taylor representation, and I would put a u into the spot where x is. So that would be e to the u, and now it would be the summation with u to the n over n factorial. And let's go rewrite that again with my red, so I could go e equals summation, where 0 goes to infinity, of a fraction that's over n factorial, and something is raised to the n. Let's put some parentheses here and here, put some parentheses here and here. There we go. U equals 2x. That's supposed to be a 2. Then 2x could go here. 2x could go here. Let's try it again. 2x could go there. And then you would start realizing, wait a second, that's in fact exactly what I have. I have a quantity of 2x over 1 factorial here. Technically, this here, 2x quantity raised to 0 would be 1, especially when divided by 0 factorial. Here's my quantity of 2x here. Here's my quantity of 2x quantities cubed here, all being divided by their appropriate factorials. So I can actually do a nice straight up substitution of 2x into this particular formula, and I wouldn't need to have done all this work here. I could literally create my formula just by doing a little substitution with Taylor series. And that's one of the strengths of knowing how Taylor series works.